Okay, students, we shall start off with CNS class. Okay. Is my screen visible? Okay. Okay. So today we shall start off with a new topic, that is base 64 encoding. Okay. So previously, which topics did we take up? Mm, CNS. I think we discussed. Okay, we discussed RSA crypto system, that is algorithm, right? So today we shall take up base 64 encoding. Okay. So by term base 64 and encoding, what do you understand? Okay, what do you understand by encoding? Hmm? Encoding, decoding. So what do you understand by the term encoding? Ciphertext. Okay. Any other definition? Okay, text with code. Okay, encoded form. Okay. So base. One sec. Okay, so base 64 encoding, actually it's a way of taking binary data. Okay, we take binary data and then we turn it into the text so that it is more easily transmitted in things like say email, then HTML form, XML documents, etc. Okay, so you can say base 64 algorithm or encoding, it's a textual encoding of binary data, you can say, that is zeros and ones, where resultant text has nothing but it consists of say letters, then numbers, then symbols say like plus, forward slash, then equals to, and so on. Okay, so the base 64 encoding, it is a convenient way to store or say transmit binary data over the media, that is the internet, and that it is specifically it is used for textual data. Okay, so then when we talk about base 64, say when we talk about number systems, that is say decimal or base 10, then binary or base 2, or say hexadecimal or base 16, so these all use a set of symbols or characters to represent numbers. Okay, now base 64, this is similar in a sense that it also deploys a set of 64 symbols. Why? To represent values, but this is not exactly used arithmetically. Okay, but it is generally deployed in computer software for encoding the binary data, that is zeros and ones. So when we say base 64, we usually mean that base 64 encoding, base 64 encoding we say. Okay, so base 64 you can say, or you can also say base 64 encoding. So 64 here you represent 64 character sets, as you can see here. So this is the base 64 index table. Okay, and the 64 characters, that is character sets, they generally consist of, say, okay, so base 64 character sets, they generally consist of, say, these are upper alphabet cases. Okay, so till 25 it is uppercase alphabets. Then again we have lowercase alphabets. Okay, these are lowercase alphabets till here. So lowercase alphabets till here, and then we have numbers, that is from 0 to 9. Okay, and then we have a plus sign and a forward, that is forward slash. Okay, and so total rounds up to 64 symbols, and this constitutes the base 64 index table. Okay, so you have to keep these things in mind. That is, you just have to remember that when we talk about base 64 or base 64 encoding, we generally talk about the base 64 index table. Okay, and what happens is, in base 64 index table we have 64 characters starting from 0 to 63, where from 0 to 25, that is how many alphabets we have in English alphabets total is 26, right? So as we are starting from 0, so it will be 0 to 25, A to Z. These are all uppercase alphabets. Then starts from 26 to 51, these are lowercase alphabets. Okay, and finally from 52 to 61, this is 52 to 61, these are alphabets from letters from 0 to 9, and then we have 62 and 63 as plus and forward slash. So total this constitutes 64 character set. Okay, so what happens is, by 64 encoding, it is the operation of converting data into ASCII text. Okay, so ASCII text format, you know, so this is the ASCII table. Okay, so it is a way of converting data into the ASCII text formats. Why? So that it can be transmitted into a text string. Say we'll talk about a text string, or say you want to hold an XML document, for example. So for that you have to first convert it into ASCII code. Okay, and these are the values for these. The symbols, again, these are the value, these are the ASCII. This is the ASCII value and this is the ASCII overall ASCII table. Okay, so this also we will use it. We will use it simultaneously. That is base 64 and ASCII table. Okay, so now what happens is, typically the input has to be a binary data. Okay, and those binary data will contain some non-printable characters. Remember in the previous class I showed you base 64 encoding and non-printable characters. So conversion to ASCII is required for this. Okay, so before it can be sent as an email attachment or say XML document or anything, you have to convert to ASCII as per required. So the way base 64 will work is, it will successively take, say, 3 characters of input. It will take 3 characters of input and it will convert it to 4 characters of output. So idea is, you have to take 3 characters of input, but then it will convert those 3 characters of input into 4 characters of output. I'll show you how in an example in the next slide. So it increases the size of the data to be stored or transmitted by 1/3. That is, because you take 3 characters of input but it gets converted to 4 characters, right? So it increases the size of the data to be stored or transmitted. But this is more efficient than just converting your input to hexadecimal string, which will double the actual size. Okay, so although hexifying small amounts of binary data is a perfectly valid thing to do. Okay, so whatever I have taught you now, I'll show you with an example. Say here, let's look at an example now. Say we have this word. Okay, we have this word A and D. this is a word, this is an input, this is our input. So what I said is we take 3 characters of out input. Okay, so 1, 2 and 3. Okay, now these characters, they have decimal ASCII values of 65, 100, 10 and 100. How? I'll show you. Say A, search for A here. Okay, we have to search now. So you have to go through this table and you have to search. Okay, so see, I got it. This is A. A is 65, that is capital A. Now look for small n. This is small n, this is 111, right? And D. So small d is this, that is 101. Okay, so A and D. So these characters, okay, so these characters, they have these decimal values, right? So now in binary we have 3 bytes represented like this. See, so this is representation of the ASCII values. Okay, now in binary we have 3 bytes represented like this. So what we do next is we reinterpret this bytes as 4 6-bit segments. Okay, so you know these things, right? Okay, just a sec. So suppose 1, 2, 4, 8, 16, 32, 64. 32, 64. 1 sec. I'll just calculate it once. 4 plus 32 plus 60. Okay. So suppose now, so these tends to, so they are taking this as 64. This is this is 110, and say this is say 100. Okay, so what we do next is, so this is the binary representation of this ASCII value, right? So next what we do is, now we interpret this bytes as 4 6-bit segments. Okay, so this is the representation, that is these are 3 segments, right? So these are 3 segments. Now we have to divide it into segments in such a way that each segment has 6 bits. Okay, it has 6 bits. So here now each 6-bit segment can hold a value between 0 and 63. Okay, so these all the 6 segments. So this is one segment, this is one segment, then this is one segment, and this is one segment, right? So each segment should have 6 bits, and the value in these segments should be such that it holds up from 0 to 63. So count this now, how much we get. This is 16, so this is 22, then this is 57, and this is 36. Okay, so these values now it will be used to derive the encoding characters to represent their outputs. So what I am trying to say is, so this part represents 16, right? This part represents 22, this part represents 57, this part represents 36. Now let's check. Okay, let's check in our base 64 index table. So what is 16 here? So 16 here is Q, right? One sec. So 16 here is Q, then go for 22. So 22 is W, then 57. 57 is 5, and 36. So 36 is K. So what will it be? Q, W, 5 and K. QW 5K. Okay. So this representation will be Q, okay, capital Q, capital W, 5 and small k. Okay, so capital Q, capital W, 5 and small k. Okay, so see, Q, W, 5 and k. So finally we get AND represents Q, W, 5 and K. Okay, so output is 3 times larger. Okay, the output, see, this is 3 times larger here. Now what we do next is, suppose we have reached the end of an say we have reached end of an input where only one character is left, say G. Okay, so I'm taking, say, one character input G as an example. So say G is left over in the input. Now G has now ASCII value of 103. Okay, it has an ASCII value of 103, and in binary we have to represent it as like this. Okay, so this is 103 and 103 is represented as this. Okay, so it is represented as this. Now what happens is, now we need to divide this into 6 segments. Okay, so ASCII value is 103. In binary we represent it as this, and now we divide it into 6 segments. So let us do it. So this. So what I'm trying to say is, you have to divide the segment in such a way that the value will hold from 0 to 63, right? So now, since we have only 1, 2, 3, 4, 5, 6, 7 and 8, so 6 bits have gone to the first segment, right? In the second segment we only have 1 left. So what we do is, in the second segment here, 0, we add zeros. So now it completes to 6 segments, right? So whenever you see the segment is incomplete in the last part, you have to add zeros accordingly. So we added 0 here, right? Now this segment now represents the values of 25 and 48. When we count this, we get this as 25 and this part is 48, right? So now what happens is, now let us look up for these values again in the index table, 25 and 48, right? So 25. Okay, so where is 25 now? So 25 is this, that is Z, and 48 is this, that is W. Yes, so Z and W. Okay, so this part represents Z and W, right? So now we have to show it in 4 segments, right? So what we do is, the next 2 parts we have to take 0, that is equal sign. Remember the equal sign in the ASCII table. So this is the lower W, this is capital Z, and the rest 2, that is these 2 segments, we have to complete it using the equal signs. Now the length of the output is a multiple of 4 bytes. So remember that the length of the output has to be multiple of 4 bytes. And what it is, first we have to check the ASCII value. So this is 103, right? So 103 becomes this in binary representation, and then you calculate it, then you divide it into this segments, into segment in such a way that each segment has a, when you count it, the total counts to a value which has to be in between 0 and 63. Okay, so this is 25, right? So it is between 0 and 63, and this is 48, right? So this value is also between 0 and 63, and then you have to look up for these 2 values in the base 64 index table, and when we checked it, we got as capital Z for 25 and small w for 48, and the rest 2 segments, because we have to have an output of 4 bytes, so the rest 2 spaces has to be filled up with assignment operator, that is the equal sign. Okay, so this is about a single input character. Now what if we have only 2 characters left over, say G and M? Suppose I'm taking, for example, so now this G, you know, it has an ASCII value of 103, we know, and M, it has an ASCII value of 109. Okay, now in binary we again have to represent it as this. So in binary form, this is 103 and this is 109. right? Okay, so this is 103 and this is 109. So representation for binary is this. Yes, now what we do, again we need to divide it into 6 segments, right? So divide it 1 2 3 4 5 6. So in this manner. Yes, so this is divided again. Now what we did is we have 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8 plus is 16. So we have 16 bits here, but we have to divide it into 3 segments, right? Because we can't leave out the bits just like that. So this 4 bit remains. So because 2 blanks are still has to be completed, so we fill it up with 2 zeros. Okay, so now this is represented in 6 segment in this way. Now what we do is, now these segment calculate the value. Okay, so this part, again this is, we know this is 25. Calculate this part, this is 54, and calculate this part, so this is say 52. Okay, so now let's look up for these values again. So 25, 54, 52. Okay, so we know 25 is Z, 54 is 2, and 52 is 0. So capital Z's 0 2. Okay, so Z 2 and 0. So this part is, so this part 25, 54, 52. 25 tends for capital Z, 54 tends to 2, and 52 tends to 0. And the last segment is empty, so we fill it up with an assignment operator, that is the equal sign. Okay, so the length now is again a multiple of 4 bytes, right? So this is all about base 64 encoding and its working principle. Now if I ask you to solve a sum, can you solve it? Say this is a word, I am taking A and D, right? Suppose take a word, say uh, take another word. Okay, I'll give you one word that is P small u and small t. Okay, this is also small p. Okay, take small p, small u, and small t. Okay, just take this as an example and try to solve it as I had said. Okay, just do one thing. Take this base 64 index table. Take the screenshot. Take a snapshot for this. Okay, take a snapshot for base 64 this index table. Have you taken? Guys, have you taken snapshot?
Yes, ma'am.
Okay, then you do is take snapshot for this ASCII table. Okay, take snapshot for this ASCII table as well.
Them are in small letter, lowercase.
Hmm?
All of them are in lowercase.
Yes,
PUP.
yes. All of them are in lowercase. Okay, have you taken the snapshot for ASCII table? So now taking these two tables into account, just solve this. Okay, that is small p, small u, and small t. Okay, now check it. Just inform me when you are done, okay? Are you able to solve the problem? Hmm? Would you all solve it? So first, what did you do? Yes? Okay. Waiting.
10, 13, 10, 18, and 117.
Hmm.
Then after that, divide it to 666. It will give us the 4 binary again in 6
Okay.
bit.
Mm-hmm.
So we have to take out value of those 6 byte binaries. What will be the next number?
Okay. So you got the fact, right? You got the concept, how it has to be solved?
Yes.
Okay. Okay, let the others solve now. We'll wait for 2 3 more minutes. Okay, the people who have finished solving it, just solve for one digit. That is, okay, 49 UW. Yeah, fine. So now take another example. Say for a single character, ma'am, after getting 100, you have to. Where did you get stuck? See, this is the solution. Okay, you take a string. Suppose put. After which step? After this step, first you took the string. So that is put, right? So put. One sec. So we took this as P, this is U, and this is D, right? So now what you have to do is you have to go to the ASCII form. That is, check the ASCII codes, what it is, and after that, uh, accordingly, you have to write it down here. That is, say PUT, right? So for P, what is the ASCII value? For P, just check. It is 113, right? Okay. So P is 113. What is okay, for what is U? 118, right? So you wrote, then for small t, okay, 117. Okay, fine. So 117. Then now what is the binary representation you got? What is the binary representation you got? So binary representation is in, you have to get 8 bits, right? So say this, okay, 11100001, right?
The coded form will be small c,
Huh?
lowercase c, uppercase x, uppercase z, and lowercase j. 4 letter.
I didn't get you.
Ma'am, the coded form answer output.
For this, for PUT.
Yes, ma'am.
Okay. Who got stuck in this step then? Just calculate this. Okay, Zahir, see, this is 1, this is 2, this is 4, this is 8, this is 16, 32, 64, 128. Now calculate. Okay, what it will be? 113 only, na? So this is not 111. This is calculated how much you got. I didn't check it actually. One sec, let me see. What is the coded form?
No,
Hmm?
actually in Google they are showing it in 7 bit,
I,
the conversion, but
hmm,
8 bit. You have to give it 8 bit,
I didn't get you.
then only they will get the answer. When they are getting error because in Google they are giving it in 7 bit, the decimal form, binary form of
Oh, okay.
13
Okay,
and
okay.
17.
Hmm. So
So
what? This has to be.
then
This is 1. This is 0. This is 0. This is 0. This is 1. Then this is 1. This is 1. And this is 0, right? So this is the coded form actually. If you take it in this way. Okay. 0, 1, 1, 1, 0, 0, 0, 1. So this totals up to 113. Again for 118 you have to check it like that. Okay. So then 8. Okay. 8 not 4 plus 2, right? So for 118 it will be um, 0 1 1 0 1 1 1 0, right? This is for 118. Okay,
yes, ma'am.
and 117 now what it will be? 0 1 1 1 0 1 0 1. Yes. Now these are 8 ones are 8, 8 to the 16, 8 to the 24. Now these 24 bits you have to divide it into 6 segments. Okay. So how it will be like? Lastly, last 2 digit you have to. Okay, these are 24. So 24, if you divide it into 6 segments, you don't have to add extra zeros because it is already total of 24. So 6 into 4 is 24. So we get 4 segments, and 4 segments again. Then when we get this, now again total this up, like when you count 1 2 3 4 5 6, so this much, how much it will be? So 16 plus 32 plus 64, so however much it will be, whatever the total value, suppose 64 plus 32 plus 16, right? So this will be 112. So what is 112 in base 64? Okay, wait, 112. 16 32 64. So this is 112. So this is not applicable actually. This is my given example. The example will be given in such a way that this part has, this value has to be in between 0 and 63. Okay, this value has to be in between 0 and 63, or else it is not valid. Okay, so I just gave this example in order to check whether you have got it or not. And the value that I gave is right. Okay. 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 But people tend to calculate it in different ways. Okay. I took this method. That is, I started from here. So I'll.
Now after conversion
Huh, huh.
after conversion of 6 bit, I got 28, 23, 25, and 35.
Okay. For this, put.
Yes, ma'am.
Okay. So you've
So
got the. Huh.
it will give lowercase c, uppercase x, uppercase z, and lowercase j.
Okay. So you got the answer. I'm not
Yes, ma'am.
getting it actually. Small p. small p here given is 113, right? So 113 we divide it, again we get this. Um, I'm not getting it actually. I have to check it again because the value has to be in between 0 and 63 or else you won't be able to use this method. Okay. So I think the in Google also they've taken this example only so that they can calculate it so that this value is in between 0 and 63. Okay, so I'll check for this bit also. mm, or else we have in exam we have to I have to calculate it first. I didn't calculate for this actually today. I just gave an example. So for exam I'll just calculate it. If it is between 0 to 63, then I'll give that question only. Okay, a valid question I will give. Okay, so did you I gave another, say for a single bit G, calculate it for, just calculate it again. Okay, I'll give you this slide. I'll share this PPT with you all. Just go through the PPT again. Okay, and try to understand the concept again. Okay, this is given step by step here. I'll erase it. Okay, so these are all given here step by step. So um, just try to go through the concept again and try to solve it, taking different examples. Okay, in the next class I'll see again. In next class I'll take up another topic. So did you understand the concept of base 64 today? Hmm? So okay, so concept is you have to take the value, you have to divide it in such a way that is it has to have however many segments. Actually it has to have 4 segments in total. Okay, so and those segments you have to divide it into 6 bits. That is one segment has to get 6 bits. Okay, say this is 8 bits, right? This is 8 bits, so you have to divide it into 6 bits. See, 6 bits, so we get 3 segments. Then again this. So and when we see here we have 2 zeros short here, that is 2 spaces short, so we fill it up with 0. So that is the concept actually. Okay, and then after it fulfills this, that is 6 bits in each segment, then you have to look up for these values in the index table, and in index table when you look up you get it as say Z20, and whatever the last segment is empty, so however empty it is you have to fill it up with 0. Okay, so this is for base 64. You have to fill it with 0, but in binary representation you have to fill it with 0 because it is binary. You have to represent it in binary form, so you have to fill up the spaces with zeros. Okay, so this is all about base 64 encoding. If any doubt, even I'll go through the example which I had given. I'll see what Gerber is there. uh, I'll get back to you people in the next class. Okay, so see you all in the next half. Okay, have lunch, we'll get back again. Thank you.